Hi everyone, welcome to Chem Help ASAP Wednesday live stream. It's really good to be back after being gone for a couple weeks. It's good to be back behind the camera again, or in front of the camera again, I should say. Anyway, this week we are going to be working on calculating enthalpy. Specifically, we're going to be calculating change in enthalpy or delta H. We are going to use three different methods for calculating our delta H's. Obviously, there are a lot more methods than just these three, but I'm going to focus on the three methods that we really use when we just want to calculate the change in enthalpy and we're not worried about, say, calculating a change of entropy or Gibbs free energy. Okay, so let's just go ahead and jump right in. All right, so we are going to start with, using Hess's law. Now, in Hess's law, we have a reaction that we are aiming for, and then we are given intermediate reactions to use to basically figure out the enthalpy change for the reaction we're going for. So this makes more sense, obviously, seeing an example. So for this one, we want to calculate the enthalpy change for this following reaction. So this is the reaction that we are aiming for, and we are given two different reactions here with their individual changes in enthalpy, and we want to get the delta H for this reaction. So the rules of Hess's law is you can reverse a reaction, and if you do that, you need to change the sign of delta H. And you can use a multiplier in a reaction, and then you would need to multiply the delta H, but by whatever multiplier you used in that reaction. So I kind of enjoy doing Hess's law. I see these as logic puzzles and trying to figure out how to put the pieces together to get to your final result. And when doing Hess's law, there are usually a multitude of ways that you can get to your final reaction. So you might be doing a step first where you want to reverse a reaction, and your friend next to you, first step might be multiplying a different reaction through by 2 or 3. And that's totally fine as long as you get to the same final reaction. Again, for our case, we're looking at this reaction right here. You can do these steps in whatever order you want. So it's really about what step do you see first, and go with that step. And don't worry if, again, the friend next to you is doing a different step first, because you can both get to the same answer. So with that being said, I am going to work through these problems in the order of the steps that I see first. So again, I think this is the third time I said it. This is the reaction we are going for. These are the two reactions that we have to work with. So when I am just looking at this information, I'm looking at a couple different things. What are my reactants and products here? Are there different species that I need to get rid of? Or maybe do I think I have a multiplier going on here? And really the first thing that I see here is there's no oxygen or no O2 in this reaction, but I have O2 in both of these reactions here. So right now, because they're on the same side, they are going to add to actually give me 4 O2. And I don't want that. I want them to add out, which means I'm going to need to flip one of these reactions. Now I can flip either reaction. It doesn't matter, but something that prompts me to flip my top reaction here is my bottom reaction already has my product in the right spot. So it already has the product I want as a product. So I would rather not flip that reaction, because that is going to make that product then a reactant. So my first step is going to be flipping this reaction, which means that I am going to multiply this reaction by -1. So, and that is going to come over here to my enthalpy for, again, this specific reaction. So what I'm going to do is I'm just going to rewrite this first reaction, and I'm going to go ahead and flip it. So my products become my reactants. And just for brevity's sake, I am going to leave out the states just so I can write things down a little bit faster. and my delta H1 now becomes negative 67.7 kilojoules. And I am actually going to cross out this top reaction just as a reminder to myself not to include this delta H in my final calculations. Okay, so now what I've got is I've got to see, all right, have, like in this case, my O2s, are they actually going to add out or do I need to do anything else? So what I'm seeing here is that I have 2 O2 as a product and 2 O2 as a reactant. So those will actually cancel out. And also my nitrogens will also cancel out because I have one as a reactant and one as a product. So I think I am good, and that is going to actually be enough. So I am, okay, let me switch back. I am basically adding these two reactions together. And to help myself, I'm going to cross out what adds out. So my O2s are adding out, and actually I think I'm going to use a different color here. And you can see that my nitrogens add out. So if I add these two reactions together, that nitrogen and oxygen are gone. I only have the 2 NO2. And again, this nitrogen and oxygen are gone, so I'm just left with my product here, N2O4. And you can see I am matching now the reaction that I want. And all I need to do is take 9.7 kilojoules and subtract 67.7 kilojoules, and that will give me my delta H for this reaction. And so that is actually negative 58 kilojoules. So let's say that you had flipped this reaction instead. Your nitrogen and your 2 oxygens would have added out completely fine. You would have been given the reverse reaction here, but what would have happened is you would have gotten a positive answer. So all you would have need to have done at that point, you would have just had a 2-step process, is you would have flipped your final reaction, which would have changed the sign of your delta H, and you still get to the same point. You still get to a delta H, again, of negative 58 kilojoules. So again, it doesn't matter the order you do it in. It's really kind of what you see first, but don't be afraid to just try something, even if it means in the end your reaction is flipped. That's totally fine because you can just flip it at the end. Okay. Great. Oh, good. I'm glad volume is perfect because it's been a couple weeks since I've been live here. Okay, so this is obviously our easy reactions. So let's do another Hess's law that is a little more complex. All right, so it's the same idea. We're probably going to need to do some flipping, some multiplying, some rewriting, all of that good stuff. So we're looking for the delta H for this reaction up here, and this time we are given 3 different reactions to deal with. And again, this is where it becomes really important to keep track of your delta H's. I like to, if they aren't already labeled as like delta H1, 2, or 3 or ABC, I like to make sure that I label them so I can keep track, because otherwise you have a lot of delta H's that are just kind of floating around your page, and it's hard to keep track of, wait, what happened with this one, and did I actually do the right math on it? All right, so again, I kind of do the same thing. I look at the reaction that I'm given, and I look at the reactions that I have here, and a couple things, excuse me, a couple things jump out at me. I have a lot of halves, especially in this reaction, so I'm thinking at some point I'm probably going to multiply through by 2 or maybe 4 or some kind of even number to get rid of those halves. And what I also see is that my N2O5 is a reactant here, and it's not a product anywhere else, and I really want it as a product here. So at some point this reaction is going to have to get flipped as well. So that's just kind of what I see at the onset. Again, I can start in either place, but what I'm going to start at is I'm actually going to flip this reaction first. So this reaction gets multiplied by a -1 as well as this delta H2, so I'm just going to go ahead and rewrite this underneath. So this becomes 2 nitric acids going to N2O5 plus water, and my delta H2, this is just a sign change, is 76.6 kilojoules. And again, I am going to cross through this one right here so that I don't accidentally throw that delta H in, or I'm not throwing those reactants and products in. All right, so now I'm feeling a little bit better. So I've got my product here, and it is a product here as well. And again, like I said, I see all of these halves right here. And so what I really want to do is I'm going to multiply this one through by 2. And this should not need to be flipped because I have my nitric acid as a product here and as a reactant here. So I actually want those on opposite sides. So I'm going to keep that the same. I'm just going to multiply through by 2, which means, of course, I'm going to multiply my H3, my delta H3 by 2 as well. So let's just go ahead and rewrite that reaction as well. So now I'm going to have N2 plus 3O2 plus H2 goes to 2HNO3, and my delta H3, if I multiply by 2, is going to be negative 348.2 kilojoules. Again, I'm just going to cross through this here so that I know I have taken care of that reaction. Okay, so I'm getting a little bit closer here. I can already see my nitric acids are going to add out. That is fantastic. But I'm seeing my waters are going to need to add out. And right now they are not adding out. They're adding together because they're both products. Now, because I've already flipped this reaction, I don't want to flip it back again, although you can if you want to. What I am actually going to do is I am going to also flip this top reaction. Again, you can see how there are a lot of different ways to do these Hess's law problems, which is why I just want to reiterate and emphasize that you and the person next to you can get to the same answer by doing things in a completely different order. It's totally fine. All right, so let's flip this top reaction. So this is going to have water now as a reactant, and hydrogen and 1/2 O2. And my delta H1, again, I'm just going to change the sign. Okay, and I am going to cross through that. All right, so let's see what I've got going on here. I think I can go ahead and add everything together, and I should get to the reaction that I want. All right, so let's start crossing out what we have, what we know. All right, so my nitric acids, those are definitely adding out, so that's fantastic. Let's take a look at water. I'll go a different color. So I have one water here and one here, so those add out. That's totally fine. Now I want to look at my hydrogens. And again, I have, oops, let me switch colors. I'm going to have hydrogen as a reactant here and a product here, and there's just one, so those also add out. Next, I'm going to look at my oxygens. And for my oxygen, I'm going to do something different. I'm going to put a little squiggly line underneath because these do not add out because I would need either 3 here or 1.5 here. But these are going to add to give me not 3.5, but to 2.5 here. So let me give here. So what I'm doing is I'm taking 3O2 and I am subtracting 1/2 O2 because it is on the opposite side. Although I think instead of writing 2.5, I'm going to use an improper fraction and write that as 5/2 because you'll see how that's going to fit in later. Okay, so let me just bring everything down and see what I've got at this point. I have 1 and 2. And again, this is 2.5, which I'm going to write as 5/2 O2. And then that is giving me just 1 of my N2O5. I'm also going to go ahead and add these delta H's. So now this is my delta H of my reaction, and I'm getting 14.2 kilojoules. So at this point, I'm going to reevaluate. And what I see is that I have the right reactants and the right products, but I don't have the right coefficients in front. But this is an easy fix, right? So this is where it's helpful to write your fractions as improper fractions instead of as mixed fractions. Because obviously if I take this reaction and multiply through by 2, then I am going to get my final reaction, which is what I want. So I'm not quite done. I'm going to take this reaction, multiply through by 2, which again means I'm going to have to multiply my delta H by 2. And then I have the reaction that I want. This becomes 5O2. And now that becomes 2N2O5. And so my final heat of reaction is 28.4 kilojoules. Okay, great. Are there any questions? Is it more likely that your enthalpy would decrease or increase in a reaction? Well, Erin, that is a very good question. That would deal more with your reaction energetics, and that is not something that Hess's law is going to tell us at this point. Now, when we get to our final reaction, we can tell if something is endothermic or exothermic, but we're really not changing things up in terms of increasing or decreasing our enthalpy. But that's a very good question, and that would be good to look at an energy reaction diagram, and you can see things like how a catalyst would change that look. But that is not what is going to be in these problems here. But thank you for your question. All right, so this is our Hess's law. We've calculated our delta H of reaction. I'd like to practice one more Hess's law. This one's a bit of a doozy here. All right, excuse me. So we have our reaction here that we're gunning for, that we want to calculate our delta H for. And this time we have 4 intermediate reactions that we're going to have to juggle to get to our final reaction. Obviously, having 4 intermediate reactions, this is a type of problem that as you start working, you might get you're more likely to get stuck and you can't see a way forward. If you're really getting stuck, then sometimes it's better to just cut your losses and start over and start with a fresh perspective. Even if like you're working on a homework problem, if you get stuck, then plan on starting over, but take a break. Either work on another subject, take a break for a snack or dinner or whatever, do something else, completely disengage your mind, and then come back and re-engage it. And a lot of times, either one of two things will happen. You'll start over and you'll start in a different place and the problem will come together. Or sometimes you'll come back to your original problem and you will see either where you've maybe made an error and you've gone wrong, or you'll see what the next step is to complete. So when you're faced with a difficult problem, please never be afraid to say, all right, I just need to take a break, not engage with this problem, and go do something else. And a lot of times when you come back, it is just so much better. So if you run up against a wall, sometimes it's better just to leave that wall alone and go do something else and then come back to it. So that is my public service announcement for tonight. All right, so looking at this problem, there are quite a few species that I'm going to have to get rid of at this point. So I'm going to have to do some reversing. I'm certainly going to have to do some multiplying because I've got 10 here and I can see my product right here. I'm going to have to at some point probably multiply again by a 10. I've got a half, which means again, for this reaction here, I'm going to have to multiply by some kind of even number to get rid of a half. What else I'm seeing is I have PCl3 in 3 different places. So like my oxygen's only in 2, chlorine's only in 2, phosphorus is only in 2 different reactions, but I'm going to have these 3 here that I'm going to have to keep in mind. So that's also what is going to make this problem a little bit trickier. So what I'm seeing first here is that I really want to reverse a reaction because I'd really like to get rid of this guy right here. So I think for my first step, I am going to reverse this top reaction. Okay, so this becomes multiplied by -1. And of course that becomes multiplied by -1, and I am going to rewrite this guy. So, oh no, actually, sorry, I'm looking ahead. I'm going to reverse that step. I think this is going to be easier. I'm going to reverse reaction number 2, not reaction number 1. Okay, all right. So, sorry, back step. Again, this is what happens with these problems. You kind of look, you think, and then like you'll second guess yourself and do something different. Again, totally fine. So I'm going to rewrite this second reaction as a reversed reaction. So P4O10, and that's going to give me P4 and 5O2. And so my delta H2 is now positive 2,967.3. That is a 6. All right, I am going to run that through there. Okay, so that's reaction is flipped. That should help with my P4. And see, this should also help with my O2, which is again why I changed last minute there, and I was going to flip that one. Okay, so now what I want to do is I think I'm going to reverse another reaction here. So I'm seeing like my chlorines are on the same side. So I'm going to reverse this reaction. Again, you might have chosen to reverse the top reaction, but I'm going to reverse this third reaction here and rewrite that. Okay, so that's going to give me PCl5 going to PCl3 plus Cl2, and of course my delta H3 is now positive kilojoules. All right, so cross that one out so I don't use it. So let's see here now. One last thing that I think I'm going to go ahead and do, and I feel like this is going to be a multi-step problem here. You know, I keep seeing this this 10 over here, and I've got nothing here, and I've got this half. So I'm going to take this, the fourth reaction, and I'm just going to go ahead and multiply by 10. Again, at some point that's going to have to happen, so let's go ahead and make that happen now. All right, so this becomes 10 PCl3 plus 5O2 goes to 10 Cl3PO, and my delta H4 is now still negative, but now it's 2,857 kilojoules. Okay, crossing this out. This, I'm not 100% there, I don't think. Again, my PCl3s are a little bit of a problem because these are going to have to add out. So what I'm seeing here right now, let me just switch to my pointer, is I've got PCl3 here, I've got it here, and I've got it here. And because it's not in my reaction here, I need these to all add out. Well, right now, I've got product, product, reactant. So I'm going to need a multiplier again to make these go to 0. So at this point, I'm thinking, what if we were to take this reaction here and multiply through by 6? Because then that would give me a 6 in front of here. And okay, I'm still using my laser pointer, but if I have a 6 in front of here, then 6 plus 4 will give me 10 on the product side, which will cancel out with my 10 on the reactant side. So that is looking like what I want to do here. So I'm going to multiply through by 6. I've got a lot going on. This is squiggly for a reason, because I'm not actually adding anything here. I'm just going to rewrite my 4 reactions again, kind of in one space. I might have to squeeze a little bit here because I'm feeling like my first reaction is like way up here at the top of the page, and then I want to go ahead and bring it down. Okay, so I'm just rewriting my first one. I'm going to try to write a little bit smaller so I can fit this in. And this delta H, again, I'm just rewriting. It is unchanged. So I am just bringing this down. These are all gone. But now I'm going to this reaction. So this is P4O10. And again, I'm just rewriting because I didn't do anything else. This is still my 2,967.3. Okay, so this third reaction, again, I have multiplied through by 6. So I'm going to change that to 6. PCl5 going to 6 PCl3 plus 6 Cl2. So my delta H3 is now, when I multiply through by 6, is, I thought I had this reaction here done. Oh, yes. Is 505.2. And then I'm going to try to squeeze in my last one, which again, I'm just rewriting here. Oh, you know, one thing I'm going to do is let's zoom up. And that'll give me, I think, a little bit more space down here at the bottom. Okay. Sorry, rewriting my fourth reaction, 10 PCl3. I'm sorry, this is getting, small, and I don't need that. O2 gives me 10 Cl3 PO. And okay, this is delta H4. This is where it's nice to have a long piece of paper to do these reactions because you're not running into this same problem. And it is very helpful to keep kind of all of these reactions together and in a row because you're adding all of these up. All right, so I'm thinking I can start adding out here. All right, so let's start with my easiest ones here. My P4 is definitely going to add out. I have 502, that's a product. This is a reactant. That's going to add out as well. My PCl3, so again, I have 4 PCl3 here and 6 PCl3 here. Those are additive because they're both products. So I have 10 PCl3 on the product side, but here I've got my 10 PCl3 on the reactant side. So these 3 together do add out. So that's fantastic. And I have, is this it? Oops. Oh, that's Cl. Okay, hold on. I wondered what this, I thought that was I2, but I just forgot to write my Cl2. Again, these are the kind of just really easy mistakes that it's easy to do and get messed up on. But That is a Cl2. I just didn't transfer it properly. So that one is also going to add out. So it is looking like this is going to give me my reaction. All right, so bear with me here. I'll do this in green. I'm going to come all the way up here, and I'm just going to write this down right here. So what I've got on my reactant side is I have my P4O10, and it's just got a 1 in it, again, just like my reactant here for the reaction I'm gunning for. So P4O10. So that is correct. All right, so I should have my PCl5 as also reactant. And yes, you can see I have no other reactants except for this 6 PCl5, which is exactly what I want. So this is looking really good. And now I go to my reactant. So let's just make sure that, excuse me, that all of my products have canceled out except for my 10Cl3PO. So that also looks good. Cl3PO. So you can see that my reactions are matching, which means at this point I just need to add all of these delta H's, remembering these negatives in here. And when I do that, I get a delta H of reaction of negative 610.1 kilojoules. Okay, whew. That was a long problem. That definitely took some thinking and some working around, but we got to our final answer, we got to our final reaction, and we got to our final delta H of reaction there as well. So let's see, are there any questions on this one? Okay, no questions on this one. Again, I'd say you're hopefully on a test, you're less likely to find trying to use Hess's law with 4 different reactions. But if you can do a homework problem that has 4 different reactions for Hess's law, then when you hit the test and you've got one with 2 reactions or 3 reactions, they're going to seem like a walk in the park. Okay, so that is calculating delta H using different reactions and Hess's law. But let's switch over and calculate delta H a different way. All right, so this is, well, I've got to be honest here. This is actually Hess's law again, just in a different format. So this is Hess's law using heats of formation for different species. So what we're going to do is we're going to use a reaction that most people just say delta H equals products minus reactants, but it's not 100% that simple. So to calculate delta H for this, when you're given your delta H for all of your species, you're going to do the sum of your products, but you need to include your stoichiometric coefficients in front of them. So it's the sum of N of the products minus the sum of, again, N of the reactants. And again, this products and reactants, I should maybe specify this a little bit more. These are the delta H's for all of these species. So you need to have access to a table. Again, this is a table that is specifically for obviously this problem right here, but you might also be working with a table like at the end of your book. Most textbooks at the very end, they'll have a big chart with a bunch of thermodynamic data, and you'll see things not only like your delta H's, but your delta S, which is change in entropy, and your delta G, which is change in free energy. So, you know, if you're using a big table, you are going to have to work a little bit harder to find all of these species, but it's the same thing. Now for this problem, again, we've got a simplified table to look at, so it's going to be pretty easy to find our products minus reactants. All right, so let's actually do this sum. So for my products, so here are all my products here, and what I'll do is I will write down my delta H's for each, and then I like to cross it off on my reaction to make sure that I get everything. Oh, and let me switch back to blue. So for my products, my first product is Al2O3. So you can see I find it here in my table and it's handy. It's the first one. There's obviously an assumed stoichiometric coefficient of 1 in front of it. Okay, so I'm going to use big brackets here for all of my products. So I have negative 1676. Of course, this is kilojoules per mole because my table tells me. All right, so that is my first product. That one's taken care of. My next product is a LCl3, which again is next here. So you can see like this is a helpful table because it's actually ordered in terms of products minus reactants. So that's fantastic. All right, and again, in front of this AlCl3, we assume that there is a 1. So it's just got a multiplier of 1, which I'm not going to bother to write down. So that's 704, again, kilojoules per mole. So I'm still summing here. That one's taken care of. Now I have 3NO. Again, here it is right here. And don't forget this multiplier of 3. That's your stoichiometric coefficient. So this is going to be 3 times our 90. Again, kilojoules per mole. That one's taken care of. And then I have 6 waters. And again, I'm given water here. So 6 times, oh, I'm going to have to squeeze this. Okay. Negative 242. And you know that's kilojoules per mole. I can't quite fit it. All right. So that is just my products. I'm going to cross that out. I am subtracting, again, the sum of my reactants. So again, another big bracket here. All right, so I'm looking for 3 times aluminum. Now, you'll notice this on the table. For all elements in their elemental form, your delta H is going to be 0. So aluminum in its elemental form is aluminum solid, so this is why it has a 0. The thing that students find tricky is your diatomic gases like hydrogen, H2, chlorine, Cl2, bromine, iodine, all of those are gases in their elemental form. Even though it is diatomic, those are still going to be 0. So that's not a misprint if you're looking again at the table in your back of your book. All right, so this, okay, let's just go ahead and write it down, is going to be 3 times 0 kilojoules per mole for aluminum. And that's aluminum taken care of. And then we're going to add in our ammonium, what is that? Ammonium perchlorate, which is right here. Again, I've got a stoichiometric coefficient of 3, so I'm going to squeeze a 3 in right there. And that is negative 295 kilojoules per mole. End brackets. So something to keep in mind when you're doing these problems is this subtract here, or this minus sign, tends to give students problems just algebraically. They don't tend to distribute it all the way across, or they just forget it, or whatever happens. So one thing that I like to do is I like to simplify each first. You can put it all in your calculator, of course you can, but I find that when I do these problems, I have fewer errors if I put in one extra simplification step. So basically, I'm going to sum my products and I'm going to sum my reactants, and then I'm going to put them together. So if I do my first bracket here, that is going to give me, this is what delta H equals, negative 3562 kilojoules per mole, and minus my bracket here. Now this is really easy because that's 0, so I'm just multiplying by 3, minus a negative 885 kilojoules per mole. And this is again where the error tends to occur. So this is minus a negative, which of course makes it a positive. So my final delta H is 2677 kilojoules per mole for this. So students tend to like this version of Hess's law, where it's just products minus reactants. But again, the place where most students get tripped up is when you have especially a negative over here, and they forget that it's minus a negative and flip the sign over again, which is why I like to put in just an extra simplification step. Okay, good. No questions. Let's practice another one of these products minus reactants. Again, it is Hess's law. It's just a different form of Hess's law. All right, so the reaction we're gunning for is right here. And again, we are given a table specific for our problem, which makes our job a little bit easier. So to write our equation, I'm going to be doing the sum of n of the products minus the sum of n of the reactants. And that will give me my delta H. So again, big brackets here. Let's do products first. All right, so we're starting with water, and there are 12 of them, so I want to make sure I remember that multiplier. Here's water right here. Again, it's the same as the other problem, 242 kilojoules per mole. The other thing that I didn't really point out, because again, we have this table here, which is so handy, is if you are looking at a larger table and you're looking for something like water, excuse me, which is very common to have either in the solid, liquid, or gas form, make sure that you're matching up, like this is water in the gas form, this is water vapor, and you're using water vapor here to get your delta H, because it's easy just to look at the first water and that may or may not actually match your reaction. So this is water vapor here. All right, so back. That product is taken care of. Now I have 9 nitrogen, so I need a multiplier of 9 here. Again, nitrogen, you can see this is a diatomic gas. It's in its elemental form, so its delta H is 0. I'm just going to go ahead and write it in just to be complete. 0 kilojoules per mole, so then I can mark that off. That's fine. And now I have 4 carbon dioxide. And again, if I find carbon dioxide, again, making sure it's a gas, that is going to be negative 393.5 kilojoules per mole. End of big bracket here. All right, because that is my last product. Okay, so that is the sum of my products minus the sum of my reactants. So my reactants are N2O4, which right here I have a multiplier of 5. Okay, that's 20 kilojoules per mole. And cross that one out. I have my other reactant. So that has a multiplier of 4, and here is my delta H. So 54 kilojoules per mole. All right, so there we go. And now what I want to do, again, I like to put my simplify step in, so I'm going to simplify in each of these brackets first. So for my delta H, my sum of my products is negative 4478 minus the sum of my reactants is 116. Oh, sorry, I dropped my unit there. This is kilojoules per mole. This is still kilojoules per mole here. Those units are important. And so then I get a final delta H of negative 4,594 kilojoules per mole. Yes, don't drop your units, because if you have done heating curve problems, especially as the one that comes to mind first, those problems almost invariably give you unit mismatch, where you've got some heats in joules and some heats in kilojoules. So just always make sure that you not only are you aware of your units, but you are writing your units down so you can make sure you don't have a mismatch. Okay, so this is our delta H. I don't know why my L didn't write. This is our delta H for this reaction. Oh, just because that's going to bother me, I want to cross that out. Okay. All right, great. No changes. We have one more way to calculate delta H that we're going to talk about tonight. And that is using bonds broken minus bonds formed. So this is, again, very similar to our products minus reactants. but in this case, you have to have your delta H's for each of your bonds. So my formula here is simply delta H is equal to the sum of my bonds broken minus the sum of my bonds formed. Okay. The best way to do this, I find, is to take your reaction here, especially this one, it's just written with molecular formulas, and translate those into Lewis structures. So you can see what the bonds are, so you can see what bonds are being broken and what bonds are formed. So what I'm going to do is I'm going to rewrite this entire reaction with my Lewis structures. So for example, methane, instead of writing CH4, I think I'm gonna need space for this. I'm going to write it such that I can see all of these carbon-hydrogen bonds. All right, plus my 2 chlorine. So I've got 1 chlorine, 2 chlorines. Now, one thing I am going to do just to make this go a little bit faster and simplify things is I am not showing my lone pairs here. So there should be 3 lone pairs around both of these chlorines. It is a good way to practice your Lewis structures if you're feeling a little rusty with that. Okay, so those are my 2 chlorine molecules, and now I have 2 fluorine molecules. And these have the same Lewis structure. They've just got a single bond here. So now I'm going to my products. And I'm going to take my CF2Cl2 and I'm going to show all of those bonds. So now what I've got is I've got carbon and it's bonded to 2 fluorine atoms and 2 chlorine atoms. Again, I am not showing my lone pairs here. Plus I have 2 hydrofluoric acid molecules. So there's 1, there's my second, and I have 2 hydrochloric acids. So that is HCl, and that is a single bond HCl. And this just makes it much, much easier to see, again, bonds broken and bonds formed. So let's take a look at bonds broken first. All right, so first I'm going to focus on my carbon, and you can see my carbon is first bonded to 4 hydrogens, and I have none of those hydrogens in my products. So all 4 of these carbon-hydrogen bonds are going to be broken. All right, now in order to substitute those chlorine and fluorine atoms on, I actually need to break all 4 of these bonds between chlorines and fluorines. So all 4 of these bonds have been broken. So in essence, for this reaction, I have broken all of the bonds in my reactants here. Now I want to look at what bonds are formed. So instead of red, let's go green. I don't really like marking through the bond because these are bonds formed, so I think I'll use a check mark instead. Again, whatever notation makes the most sense to you, go for it. Okay, so these carbon-fluorine bonds are new. These carbon-chlorine bonds are new. These hydrogen-fluorine bonds are new, and so are the hydrogen and chlorine bonds. So again, I've taken my reactants, I've broken all of the bonds, I've formed products, and all of the bonds there are new. So now it's just a matter of taking the energies of these bonds and adding up bonds broken, bonds formed, and then subtracting the 2. All right, so same thing for when we were doing products minus reactants. I'm going to use big brackets here. All right, so what I've got is I have 4 of my carbon-hydrogen bonds have been broken. So 4 of these bonds have been broken, and those are 413 kilojoules per mole. I have other bonds that have been broken. I have 2 of my chlorine-chlorine single bonds, and those have an energy of 239. So 2 of these at 239 kilojoules per mole. And I also have 2 of my fluorine-fluorine single bonds, and those have an energy of 154. Again, kilojoules per mole. Okay, so that is all of my bonds broken. And now I need to add up all of my bonds formed. So for my bonds formed, I have 2 carbon-fluorine single bonds. So here's carbon-fluorine single bonds. Those are 485 kilojoules per mole. And I have 2 carbon-chlorine bonds. So I have to add those in. Those are 339 kilojoules per mole. Okay, let's keep going. I have 2 hydrogen fluorine single bonds. Just again, I'm just pulling from my table here. These are not numbers that like you would ever be expected to memorize, although if you do a lot of these, you might find that you inadvertently memorize them. And I have 2 hydrogen chlorine single bonds. So this is a 2 and a 427 kilojoules per mole. Oh boy, I'm squeezing again. Okay, and brackets. And just like I did with products minus reactants, I like to have at least one simplifying step. So what I have just simplifying within the brackets first is 2,438 kilojoules per mole. And that is going to be minus 3,632 kilojoules per mole, which is then going to give me an overall delta H of negative 1,194 kilojoules per mole. I will put this in a box so that if I was writing this as a student and handing it into my teacher would be able to find it pretty easy. Okay, so that is how we do delta H with bonds broken minus bonds formed. I think we have just enough time. I'd like to do one more of these just for extra practice. Again, this is the same idea. I have a table here and it's given me all the bond information that I need. But again, you might be working with a larger table. It just depends on what you've got going. I am going to, well, let's first just write our mathematical equation. Sum of bonds broken minus the sum of bonds formed. And let's do our Lewis structures here so we can actually see our bonds in the first place, and then we'll be able to determine which ones have been broken and which ones have been formed. All right, so my C2H4, that is actually going to give me a double bond. So I have got carbon double bonded to carbon. For those of you who know a little organic chemistry, this is ethene. Now I've got ozone. That is an oxygen, double bonded to an oxygen, single bonded to an oxygen. Again, I am leaving out lone pairs here just for simplicity's sake. And here I'm going to form this monster again. I know what this is, but it is good practice to practice with your Lewis structures if you are less familiar with them. All right, and this is another reason you can see, just kind of as a side note, how this Lewis structure translates to this molecular formula. Instead of, you could write it as C2H4O, but writing it like CH3CHO gives you a little bit more of a hint as to what the Lewis structure is, which is actually really helpful. Okay, and plus, excuse me, O2. And of course that is an oxygen double bonded to an oxygen. All right, so now that I have all of my bonds, again, it's going to help me be able to determine which bonds are broken and which bonds are formed. So I am definitely breaking this carbon-carbon double bond here. That is absolutely going to be broken. And you can see that these carbon-hydrogen bonds, I still have these carbon-hydrogen bonds in my product, so I'm actually not breaking those at all. And I have, let's see, 1, 2, 3, 4 carbon hydrogen bonds, and in my product I have 1, 2, 3, 4. So even though, yes, this hydrogen has kind of, or maybe you can say this hydrogen has rearranged, you still have 4 carbon hydrogen bonds in the reactant side and 4 carbon hydrogen bonds on the product side. So it doesn't matter in terms of this equation right here that they may be bonded to different carbons. You still have that carbon hydrogen single bond. Okay, so I'm not breaking any of my carbon hydrogen bonds. And for oxygen, I am keeping this double bond and I am breaking this single bond. Excuse me. All right, so those are my only 2 bonds that are broken. So let's take a look at what bonds are formed. Okay, so my new bonds that are formed are my carbon-carbon single bond. So I broke my double bond, I have formed a single bond. Another new bond that I have is this carbon-oxygen double bond. That is a new bond. This oxygen-oxygen double bond is actually not a new bond. That is the same bond. So those are my 2 bonds formed. So when you first look at this reaction, you might think you've got a lot of bonds broken and a lot of bonds formed like our previous one. But again, you have to be really careful and follow the Lewis structure and see how many you have of each. We actually just have 2 broken and 2 formed. All right, so let's plug our numbers in. Okay, so we have our delta H. And let's do our big brackets here. Okay, so our bond's broken. We broke this carbon-carbon double bond. There's only one of them. And you can see it has a delta H of 614 kilojoules per mole. The other bond that we broke was this oxygen-oxygen single bond. And here is its delta H. So that is 146 kilojoules per mole. And I think I can squeeze this in here in one line. Haha, it's very exciting. Okay, so our bonds formed. We formed 1 carbon-carbon single bond. So here's my single bond. That is 347 kilojoules per mole. And our other bond formed is our carbon-oxygen double bond. So that is 745 kilojoules per mole. All right, so again, just this one maybe be easier to not simplify in the brackets, but that doesn't hurt to simplify in the brackets. So our delta H is going to be 760 kilojoules per mole minus 1092 kilojoules per mole, which will give us excuse me, an overall delta H of negative 332 kilojoules per mole. Again, I'm going to put it in a box so it's a little bit easier to find. So that is our delta H for this reaction using bonds broken minus bonds formed. Now, yes, there are other ways to calculate delta H, but most of those other ways can involve just other things like, again, maybe entropy and free energy or something like that. These are how we calculate overall delta H's for a reaction, kind of using either delta H of formation or, again, delta H of bonds or delta H of intermediate steps. So, again, this is kind of our 3 main ways of calculating delta H. Anyway, are there any okay, there are no questions. That's fantastic. I hope you guys found this helpful. Thanks so much for joining me this week, and I hope to see you next week. Good night.